Hello, everybody. So now we are going to discuss one important thing, which is related to defining the quantities that we have, and to talk about what we mean by these two terms: the molar or mass rates and the mass and moles. I'll give you a very simple example with these two to compare these two images that we see here. So the first image here is a container that contains a specific amount of a liquid. Let's say it's water, and in the figure to the right we have a tube or a pipe where the same liquid, which is water, is flowing in and out of the tube. And the question here is, how can we define the amount of water in these two cases? If I have or I need to define the amount of water, I want to know how much water we have here. How can we define them? So for the first case, it's a simple case which we are all familiar with. We can define the amount of water by more than one method. First is by or using more than one parameter. The first is the mass. I can say that I have 1 kilogram, I have 1 liter, I have I mean, so 1000 gram, whatever the units that we have. So one way is by using the mass. The second is by the volume. I can say I have and this is what we usually use in the water bottles. You buy a bottle of water, it's either 250 milliliters, 500 milliliters, 1 liter, 2 liters, whatever. So it's defined by volume. The amount of water is defined by volume. The third case is the number of moles. I can define the amount of water by saying that I have in this container, let's say 1000 gram moles, 2000 gram moles, whatever the number of moles. So these three three parameters are used to define how much water we have in this container, which is a very, very well-known thing. The second case is different, a bit different in a sense of that the amount of water that we have here was constant. It's the same. It doesn't change. But in this case, we don't have a specific amount of water in the pipe. The amount of water that we have now are going to be drained and replaced by another amount of water after 1 minute, after 2 minutes, whatever the amount of time, but it's not the same. So if I want to define the amount of water that I have here now, it's going to be different from the amount of water that I have later, because the amount of water I was talking about is not here anymore. And this is because there is change with time. The amount is changing with time. So to be able to define it, we define it using another parameter that we call a flow rate. So the flow rate is representation of how much of this material is flowing inside this tube or this pipe per unit time. So I'm saying, let's say that I have in this tube I have 1 liter per minute. So each minute 1 liter flows through this pipe. So this is a volumetric flow rate. So we have the same three parameters, but they are going to be defined as the parameter per unit time. So I have mass flow rate, so how many kilograms I have per unit time, or volumetric flow rate, so it's liter per time, and the molar flow rate, how many moles per unit time. So this is the main difference between these two, and this is a very important thing. In our chemical engineering applications, we deal in majority of our cases that we deal with are flow rates, especially in the chemical plants or in any process. You have a continuous flow. It's not something you just put and keep it in a place. It's always flowing. So that's why this is important to know that to know how to define a quantity that's flowing compared to just a static quantity. So the rule here is that the flow rates are used for flow streams that have flowing components. Masses, volumes, and moles are for static components. I'm here again. There is one thing here just to be a note for you, that the units that I have here, the kilogram, the liter, the gram, moles, and the second, are, for example, it's not only these units. You can have pound per hour. You can have foot cube per minute, you can have pound mole per millisecond. It's any unit of mass or volume or moles per any unit of time. So there is one more question that might come here, that in this case, for example, let's take the simple case for the mass, volume, and number of moles. The amount of water is the same. It's constant. It's not changing. So if I define it by mass, somebody defines it by volume, somebody else defines it by moles. Are these three numbers different, or they are related? Since we are talking about the same thing, the same quantity, the same amount, then there must be related somehow. And if I define it as mass and you define it as volume, there must be a relation between these two, because it's the same quantity anyways. I'm not talking about two different things. It's the same thing, whether we define it by mass or volume, it's the same quantity. So we can get together by having some sort of relation between the mass and volume, the mass and number of moles, and the volume and number of moles. And this is what we are going to discuss in the coming slides, that how can we get the relation between the mass, the volume, and the number of moles. So we will take first the relation between the mass and the volume. And this is pretty simple and well-known thing. The parameter that relates the mass and the volume is the density, and the density has the dimensions of ml power minus 3, which is mass per unit volume, and the density equals mass per unit volume, and from this we can calculate the mass from the density and the volume, and the volume from the mass and density. This is a high school thing, we all know this information. We can apply the same concept or the same relation to the rates, and still the equation is going to be valid, and the units are homogeneous. So we can do this by saying that the density equals the mass flow rate over the volumetric flow rate. So in this case it's kilogram per second over meter cube per second, so this second will cancel out and the result would be the same. So we don't have a density rate. Density is a physical property, it has nothing to do with the flow. So the density can be mass over volume or mass flow rate over volumetric flow rate. And we can rearrange the equation to be mass as density multiplied by volume, or mass flow rate equals density multiplied by volumetric flow rate, or the opposite. And again, the dots here that we put are just for differentiation between the quantities and the flow rate. There is one more thing we need to discuss here, which is a new parameter. You might be familiar with this, but in case you didn't hear about this before, this is a parameter that's called specific gravity. Specific gravity is the ratio of the density of any substance to the density of a reference substance. So let's say that, or there is already a material that is taken as a reference, and it's a well-known thing. It's a very, very, very famous number. So we know this number. So it's a constant. You can assume that this is constant. So if you know the density of any material and you divide it by the constant, which is the reference density, you can calculate the specific gravity. So now you might ask yourself a question: why do we make this parameter? Since we already know the reference density and we know the density, so there might be no point of this. The point is that the specific gravity has no dimensions. It's density over density, so it has no units and no dimensions. This means that the value of the specific gravity of any material is going to be constant regardless the unit system you are dealing with. So if you are using the SI units, the CGS units, the American unit system, whatever the unit system you are using, the value of the specific gravity will not change. Okay? And this is one thing we like in chemical engineering, which is using dimensionless quantities. The quantity that has constant value regardless the units is something that we really love. And in many references and textbooks, you would see tables for physical properties. In a lot of these tables, you would see that the density is not put in the tables. It's replaced by the specific gravity to rule out the effect of the units on the value. And in order to get the density from specific gravity, it's just as simple as rearranging the equation to calculate the density by multiplying the specific gravity by the reference density. The reference density is a very simple one, which is the density of water at 4 degrees Celsius, and this is for solids and liquids. For gases, it's a different thing that we are not talking about here, but for solids and liquids, it is density of water at 4 degrees Celsius, and luckily it is 1000 kilograms per meter cubes, or 1 gram per centimeter cube, so it doesn't require any hard calculations to get the density. If you know the specific gravity, you can just get it by very simple calculation. It might be tough if you're doing this using the American units, because the density is 62.43, so you need to do the math yourself. So this is all for this video. We will continue next video to discuss the way we can convert from number of moles to mass and volume. So see you then, inshallah. Goodbye.